I did training, so
Can you share your screen?
카메라 스케줄 확인. Sorry.
It's close to the video and voice icon.
Yeah,
So
it's
there
on
is
the bottom left corner.
yes.
Looks like a computer. There's this icon looking like a computer. Okay, so I think maybe we need to first start the session because it's already the time. So hello everyone, I'm Jie Zhang from University College London, and I'm really glad to be the chair of this session, which is about synthesis and analysis. And we have 5 speakers today. I think that not the slides. So we have 5 speakers today to introduce 5 papers, and it's from a technical track and also from the software engineering industry track. So the format is that we will first have the talk one by one, 5 minutes long. Yeah, we can see your screen well. Thanks.
Okay.
So each talk will be 5 minutes long, and after all the talks are given, we will then enter the Q&A session to answer the questions from the audience and also have some further interesting discussions if there is enough time. So let's go to the talk. The first, I think we just follow the order on the ICSE webpage. So the first one will be Sanfen from Facebook US. Introducing their work analyzing CMake build system.
My voice is echoed.
You need to unmute yourself.
Should I stop my?
I think for every speaker who is not currently speaking, please unmute yourself in case other people may hear echoes.
I cannot see my slide.
Tayoshi, can you please stop sharing your screen?
Stop sharing your screen.
Stop sharing.
Yeah, we can see your slides now. So.
Okay. Hi everyone. My name is Shang. I work at the WhatsApp security team at Meta, and today I'm going to talk about some challenges when analyzing CMake build system. The first question is, why do we need to analyze CMake?
Okay.
So to give you some context, so there are 2 billion people using WhatsApp every day. So security is very, very important for us. And unfortunately, this popularity also attract a lot of attackers, and these people are very talented. They are well-funded, well-organized, and many are even backed by some foreign governments. And the most serious attacks happened like 3 years ago when the NSO group, they can execute random code on the user phone. And what they did is they exploited a buffer overflow in the WhatsApp VoIP library. So what we do to prevent similar attack from happening again? So we use linter, we use fuzzing, we use tail analysis. So there are nothing new here. We own our techniques to discover memory corruption bugs. So when we start trying to doing this, we see some challenges. The first one is, for example, when we want to do fuzzing, and Facebook already have a fuzzing pipeline when they run the fuzzing on the cloud and they upload the corpus. They have the coverage of each function, and everything is run by Bug. And Bug is a default build system at Facebook. It support for all the languages, and it's have some cache system. It's very efficient, very popular. But for us, like WhatsApp, we we develop at a separate company, and so everything will be on CMake. So when we start to do we want to first a library, the first thing we need to do is we need to convert CMake to Bug. And this is very expensive. To give you an idea, a very experienced software engineer need to spend like 1 month to convert the WhatsApp voice from CMake to Bug. And not only they need to do the manual conversion, they also need to maintain it every day, because if the engineer they update the CMake file, then this person need to manually maintain the Bug file. And this not only happened to WhatsApp, but also the other companies that bought by Facebook, by Meta. For example, if you know the Metaverse, the Oculus, they still using the CMake file, and some other company. So CMake is kind of popular in the industry, but here at Facebook, we only use Bug, so we always have to do this conversion. The second use case is if, for example, if an engineer they upload this code, so this code have a buffer overflow vulnerability when the user control data is go to memcopy, and memcopy is can copy over the bound. Unfortunately, in the CMake, this bug can only this file can only include it when the flag full is unable. And when we run static analysis, the first thing we do is we need to convert source file into abstract syntax tree. And if this file is not included in the set of build file, then there's no way for static analysis to recognize, okay, this file to find this vulnerability. So we need to somehow like look at the CMake file, and for a file, we need to define the compilation flag to know that, okay, with this kind of command, we can have this file. So out the scope of this talk, but we are trying to develop a symbolic execution for CMake to address this problem. And when we're trying to do to analyzing CMake, there are some challenges. The first one is the scope of the variable of a function. For example, if we have a Python function like this one, we definitely know that the function bar will not change the variable a because it doesn't take any parameter of a. But in the case of CMake, it is different. Bar can change the value of a, and actually it due to some variable expansion, the scope of changing can be much more complicated. The second thing is nested variable expansion is a totally nightmare. So in this example, if you see like at line 4, where we have like full and bar is set to x, and then we set at line 1 we have full and bar set to x, and then at line 4 we have some full var bar 7, which will expand to full and bar, and that's why it go to x. And then that's why when we mess it h, it is set 7. So when you do symbolic execution, for example, you only have like one symbolic variable and assigned to some value, but here we have several symbolic variable. And the second thing about variable expansion is depend on there are only one data type, and it's a string, but it can be considered at list. So depend on the context where it is considered a list of string, the variable expansion can act in different way. And you see like the expansion in this example, it totally a mess. And another thing is when we want to do symbolic execution, we need to solve the constraint. And as I said, solving the string constraint is already difficult. And here we can have a string that can have list of operator, and we cannot have existing decision procedure or SMT solver can handle this kind of string and list constraint. So conclusion, so I just show you why the need to program analysis of the CMake build file. And the reason that I'm giving this talk is I couldn't find any existing work on CMake, and analyzing the CMake is very hard, and we want to have more attention from both academia and industry. Thank you for your attention.
Thank you very much. So our next speaker is Toyoshi Nakijima. Sorry if I pronounce your name incorrectly. From Shibaru Institute of Technology, Japan. Please go ahead. So the work is about a software impact analysis tool based on change history learning and its evaluation. Hi, can you hear me? Toyoshi, can you hear me? I don't know whether it's because I pronounced the name in a bad way.
Hi, Tsuyoshi. Hi, Tsuyoshi. Can you hear us?
Can you hear me?
Okay, dear, can you please ask the next speaker to present? I'll send a direct message to Tsuyoshi.
Yeah. Okay. So we'll temporarily skip this talk and go to the next one from Chen Zhuangbing, Chinese University of Hong Kong, China. So the work is about adaptive performance anomaly detection for online service systems via pattern scratching.
Okay, sure. Thank you.
Yes.
Okay, so I will do the presentation. Hi, everyone. My name is Zhuangbing Chen from the Chinese University of Hong Kong. Today, I will paper entitled Adaptive Performance Anomaly Detection for Online Service Systems via Pattern Sketching. Nowadays, are everywhere. For example, Google Suite, Office 365, they have been increasingly integrated into our daily lives. Performance anomalies, performance degradation issues of online services. For example, slow service response. They are potential threats to business revenue and customer satisfaction. To ensure the performance of online service systems, they are closely monitored with various software and system metrics, such as request latency, traffic volume. Performance anomaly detection is observations that deviate significantly from the general distribution of data. Time series anomaly detection is a and indeed, many approaches have been proposed in the literature. Compared to them, our approach can better meet production requirements thanks to the following advantages. The first is interpretability. That is, our approach can explain what performance issues an anomaly represents. Interpretability can help gain engineers' trust on the results and accelerate failure understanding. The second is learning. Many existing methods need to retrain the entire model to accommodate and fight against possible concept drifts. Finally, our approach provides a way to accumulate human knowledge, which is a valuable asset for a company. Our approach is based on the key observation that an anomaly is dissimilar to normal data while similar to anomalies of its kind. In this metric time series, where anomalies are in red, we can see normal data parts do not look like any of the anomalies, but we have two pairs of similar anomalies. Based on this observation, we have three main tasks. The first is to automatically extract metric patterns. We mean similar subsequences. For example, these four anomalies constitute two metric patterns, pattern 1 and pattern 2. We also have other patterns like pattern 3, which are formed in normal periods. We can see a metric pattern can be either normal or abnormal. So in task 2, we need to distinguish them. These patterns can be used to detect anomalies. Finally, we can label the performance issues associated with abnormal pattern. By doing so, when the detected, we can intermediately recognize what have happened. We call such a design pattern sketching. Our performance anomaly approach is called AD Sketch. Main components in AD Sketch. The first is metric pattern discovery, where we also conduct offline anomaly. This is like training a model with offline data. The second is online anomaly detection. This is like deploying your model in production environments, where metric time series come in stream. In this case, the parameters and data of your model are fixed. The final one is learning, where the model gets updated while doing online. In the evaluation part, we address the following 3 research questions. Is the effectiveness of AD sketches offline, online, and adaptive anomaly detection? The results show that AD Sketch outperforms state-of-the-art approaches. Also, it has been deployed in production and demonstrated practical benefits. This is the end of my presentation.
Thank you. So, Fushi, are you ready to share your screen to introduce your work? We can't hear you, Jiawei. Are you trying to speak?
Hi, Tsuyoshi. It looks like because the speaker did not respond to my message, I'm not sure if he has. He can listen to us.
Okay, if the audience, if any other author from the paper, a software impact analysis tool based on change history learning and its evaluation, please try to contact Tsuyoshi, or just go ahead to unmute yourself to introduce your work.
Yes. Do we have audience from one of the authors of the paper Software Impact Analysis Tool based on change history learning and its evaluation?
Could you check the author from the audience list? I will introduce the next talk. We need to go ahead because due to time limit. So our next talk is from Cong Li from Nanjing University, China, to talk about push-button synthesis of watch companions for Android apps. Please go ahead, Cong. Please unmute yourself.
Okay, can you see this?
It's not your slides.
How about this?
Now it's
okay,
now
cool.
It's fine.
Okay, cool. Okay, hello everyone. My name is Hong from Nanjing University, China. Today I'm going to share with you a very interesting application of program synthesis. Let's port your favorite app to Android Watch. Indeed, we are interested in this problem because there are too many watches today, but there are not so many apps for us to use. Indeed, this forms a big gap between smartwatches and its convenience. So what we are trying to do is try bridging this gap by something like app synthesis or companion synthesis. And this is our whole picture. On the left, we have the app on the phone, and on the right, we have our app that we'd like to synthesize on the watch. And our approach is looking like doing a jigsaw that we firstly disassemble the app to many widget pieces. From all of them, we just select part of them, and then we migrate and recompose them on a limited watch screen. Indeed, we separate this problem as 2 sub-problems. First, we have to decide which widgets to select, and then we have to decide how to position these widgets or compose these widgets on a limited watch screen. And formally, we need to find the functions f and g. For widgets that f returns false, we directly drop them. And for widgets that f returns true, function g to decide the exact position x and y on the watch screen. However, it's never easy for machine to know which widgets to migrate from totally scratch. So, but the UI design follows spatial locality that we can learn from examples like this. Like here, you may notice all the digital widgets have the same parents. other operators also have the same parents and similar tree structures. So if we are known that non and plus examples, so we should migrate all these highlighted widgets. And that's the high-level idea behind our function f, which we call widget selector. It can select properly matching widgets level by level along the layout tree. Like this one, it can select all the highlighted widgets in this tree. And our goal is to synthesize such a selector from all these examples to select all the positives and reject all the negatives. And our approach just takes the vern space algebra to do this synthesis work. And in this case, the vern space of every single widget, every single example widget, is a set of all widget selectors that each of them can select the target example. Then having the vern space of every example, we just intersect the vern spaces of our positives and subtract the vern space of our negatives to get the final vern space. Since there may be multiple selected in the final vern space, we then rank them and get our optimal one as our function f. Yeah, like this one. As for function g, we just take a very sophisticated approach that we model the watch screen as an m times n grid. And our goal is to position every widget on this limited grid into a specific cell. For this goal, we just collect the position relations from the phone, like which none should be to the top and to the left of widget 5 as many constraints. And we feed these constraints to the set solver to get their positions. Okay, let's combine them together. In this work, we disassemble the problem as two functions f and g, where f decide which widget to select and model as the selector. G decide the exact position x or y on the watch screen, which is modeled as a grid. And combine them together, we can get our final companion. And these are some examples of our synthesized companions. You may notice some successful ones look quite good. Yeah, indeed. But some failed ones looks not, yeah. Like this one, it just select a widget that we don't want to migrate, and this one just fails to render the web view. Yes. Okay. Today we have shared with you a very interesting program synthesis application called Jigsaw. Indeed, we do not intend to solve the companion synthesis problem once and for all. Actually, it still has many limitations, and there's a long way to go. But we hope Jigsaw to attract many research attention in this direction. Yes, that's all. Thank you.
Thank you, Tom.
Okay.
Our next speaker is Tsuyoshi Nakajima from Japan, talking about their work, a software impact analysis tool based on change history learning and its evaluation. Please go ahead, Tsuyoshi. Wait, come. Great. Please unmute yourself. Please, yeah, let me type my message in the chat window. Hello.
Can you
Great.
hear me?
Yeah,
Hello?
great. We can hear you now. Great.
Hello.
Please go ahead.
Hello, everyone. I'm Tsuyoshi Nakajima, Shibaura Technology. Today, I will talk about the software impact analysis tool based on change history learning and its evaluation. First, I would like to talk about the background of this work. Software change impact analysis played an role in controlling software evolution, especially for many projects working on the same large source code base. The key importance for the analysis is to improve and efficiency in creating an application without depending on developers' knowledge. First, the target project are software development of continuously evolving product working on one large source code base. About 30 projects run every year. Each project has 10 change requests on average. So approximately 300 change requests are generated every year. The problem is that many small projects run in parallel with shortage of human resource. The target project strictly follow the rule that one change design document, including requirements and the change on source code, is created for every change request. The number of the components in the source code base is 32. Over 1,000 documents have been accumulated. This slide shows our approach. We developed a tool to machine learn many change design documents to application candidates to a new change request. This figure shows the configuration of the machine learning components in our tool. The tool firstly extracts text of the change request written in Japanese from the change design document and translate the text into a vector form using a word embedded technique. Secondly, it modified the component's name and then convert them into component vector. Each element of the vector is 1 when the component is modified, or 0 otherwise. Since the component vector has multiple label to be classified, this machine learning is categorized as a multi-level classification problem. For the multi-level classification, metrics for evaluating single-level classification, such as accuracy, recall, and precision, cannot be simply applied. So we introduced 2 new metrics, cover ratio RC and accuracy in the coverage range AC. I skipped their explanation. So we did the experiment to evaluate our tool. The figure shows the data size used for the experiment. 5 change design documents are used in total, and 325 for training data and 80 for test data. Result of the experiment shows fairly high performance. The coverage range less than 20% for all the implementation of vectorization on average. This means that modification target can be covered by reviewed 1/5 of the candidate on average. In addition, the accuracy in coverage range 50%. This means that more than half of the reviews can find the modification targets correctly. The result indicates the proposal can significantly reduce the workload of impact analysis. This is a conclusion. That's it. Thank you very much.
Thank you very much. So next is our last talk from Nanman Jin Microsoft Research Indian. So he will talk about Jigsaw large language models meet program synthesis.
Hi, yeah, can you hear me?
Please go
Okay,
ahead.
yes. Thank you. Hi, everyone. So I'm Naman. I'll be giving a talk on Project Jigsaw, where large language models meet program synthesis. This is joint work with Skanda, Arun, Naga, Suresh, Sriram, and Rahul at Microsoft Research India. So you might be aware that nowadays we can generate code from these large language models. Basically, you give them natural language description of some intent task, and they'll generate some code for you. However, the code that these models will generate, it will only be hopefully correct because these models trained on web scale data, they do not understand the syntax and semantics of programs, and they do not provide any guarantees. This is because GitHub Copilot, which is the pair programmer from GitHub, the website itself suggests that the code suggested should be carefully tested, reviewed, and vetted like any other code. And these issues are going to lie even if we fine-tune these models or build bigger models, get better data sets. The vetting process is a necessity, and the burden of this vetting will fall on the users. So this is where the Jigsaw hypothesis lies. We believe that if we augment these models with guardrails based on program analysis or synthesis-based techniques, we can automate some of this vetting and make the users more productive. So if we can help the users in understanding some of the code or giving them some guarantees on the code that is produced, then it shares the burden with the user and will help the users in the long run. So let me outline the Jigsaw vision for you. We have these 4 stack components with inputs, pre-processing, the model, and post-processing. So let's look at these one by one. So at the start, you'll see some inputs. At the top is the natural language description, which was common to the language model as well. But you'll see we also take in some additional specifications. These might be input-output examples, like for table manipulation, for instance, or static analysis specifications. And once we have these inputs, we'll send them to the pre-processing module, which will set the appropriate context prompts for GPT-3 or Codex or any other language model. So since these models require a few short learning setup in which you give them some example of the task you want to do, so the pre-processing module builds that prompt for. Next, we send these the pre-processed input to these models. Note that we have this plug-and-play architecture where you can use GPT-3 or Codex or any newer model that you want to use. Once we have the output from GPT-3 or Codex or whatever the language model is, we'll send them through our post-processing module where we'll use our program synthesis or analysis-based techniques to give guarantees and also repair some of these outputs based on just like program repair techniques, the traditional program repair techniques. Finally, we send the results to the user. It might be a correct program, or the user can edit the program and make it correct. In such cases where Jigsaw wasn't able to find a solution, we can learn from this user feedback and improve over time. So for the next user, we might perform better. So let me try to show the Jigsaw vision with an example for Python Pandas task. In case you're not aware, Python Pandas is a Python library for table manipulation tasks. So a table manipulation task might be, if you look at this example on the left-hand side, you're removing a prefix from the first column of the table. So this is a table manipulation task. And if you're just using a language model, you'll probably write something like this to the model: remove substring name colon from the column C of df, and you'll send it to the model. In that case, model will generate some code for you. However, it won't even tell you if the code is correct or not. And in this case, the code is incorrect. And to realize it, you might be trying it on some input-output example, like we can see here. Instead, if you're trying to use Jigsaw, then you'll use this input-output example itself as an input to Jigsaw, as I mentioned, the additional specification, and you'll pass it to Jigsaw. Now, there are 2 cases that are possible. In the first case, Jigsaw itself can find the correct solution. And in that case, we'll inform the user that this solution produced is correct on the input-output you provided and is hopefully useful in your scenario. The other case is still possible that even Jigsaw is not able to find the correct solution. In such cases, we expect the user will give the user some estimate or guess of what might be a correct solution based on the model outputs. And the user will probably search around and try to fix it. And once the user fixes this, we'll also learn from this user feedback and improve over time. So in case a future user asks a similar query, maybe he's trying to remove a different substring on a different column with a variable, different variable name, learning from feedback will still work, and we'll be able to solve the task for him. So this is the whole process of using Jigsaw. Let me end with an outline of the results. So we built a multimodal robust synthesis system for large API with more than 100 functions. And our key insight on the post-processing module was that we were able to find that different language models were failing in similar ways. So we found that both GPT-3 and Codex produced variable name mistakes. They were making argument mistakes where some argument was wrong, or they had some mistakes that the code was almost correct and lied within some small AST rate distance. So based on these insights, we repair these model outputs for different failure modalities via generic transformations and are able to improve performance significantly. So yeah, that was my talk. I hope you read the paper and feel free to ask any questions. Thank you.
Thank you very much for all the talks. So next we will enter the question and answer session. Could every speaker unmute yourself? I think we are missing, yeah, and also Tuji. Jiawei, could you type a message in the chat window to remind him? Thanks. So we got a question on Jigsaw. So it's from, sorry if I pronounce the name incorrectly, it's from Jesse Klim. So the question is, two questions. First one is, you stated that huge language models lack program semantics comprehension. Does this imply that a network model using deep learning can't comprehend the program's intent? Maybe you can first answer this question and we'll then go to the next one.
Hi, yes, sure. So the question is, can do these language models comprehend program semantics? And that's a very interesting question. So there was a recent paper from Google. So it was around the same time when the paper on Codex was released, where they actually demonstrated that if you try to train a network to predict the output of programs when explicitly trained on a huge set of programs, they found that the model didn't learn anything and produced very low accuracy, less than 20 or 30%. So these models definitely do not comprehend semantics, since they are not able to execute them even with sufficient training.
Thanks. So the next question, your research appears to focus on the pre-process, post-process, and user feedback phases. Can you offer your knowledge regarding which area of testing on your machine requires the most processing resources, like CPU, GPU, and memory?
Yes, definitely. So maybe I'll just outline all the modules and the processing requirements. So the pre-processing module is fairly light, where we just do text-based similarity, and we are able to do that fairly quickly. In the post-processing phase, we are using program synthesis techniques that sometimes require enumerative search or some kind of deductive logic. In those cases, we require some CPU computation power, especially for the enumerative searches. And we do not use GPUs for our pre-processing or post-processing.
Thanks.
Does that answer your question?
There's a follow-up question.
I think so, yeah. There's a follow-up question. Considering Jigsaw's post-processing outcomes, can we conclude that optimizing post-processing among pre-processing and post-processing is a successful strategy for enhancing accuracy? So in the case of GPT-3, the accuracy of Jigsaw appears to be significantly higher than
I think that's in the section.
Yeah. I'm curious about the root cause, so probably you could explain about root cause for for the superiority of your proposed approach?
Yeah, sure. Let me just reread the question once more. Meanwhile, yeah, maybe someone else can.
So another question is from Sanfran. I think you can just speak. So the question is, did you consider user experience when synthesizing apps for smart watches? Oh, this is actually another Jigsaw paper. That is the one titled "Push Button Synthesis of Watch Companions Android Apps." So I think it's a question for Tony, right?
Yes.
Yeah.
Yes,
Go
yes.
ahead.
Yes, as you said, user experience is a very important question for app synthesis or companion synthesis. But Jigsaw, first, today, but at present, our prototype just focus on the functionality instead of user experience because it is already hard to make the tool work. But yeah, we are working on to make the user experience more better and better. Thank you very much.
Thanks.
I don't know if I should ask here directly because, for example, if you have two buttons, you can organize like one on the left or the other on the right, or you can like reverse the order of the two buttons. So when you do this conversion from, for example, for the phone to smartwatch, how can you determine the position of the button, for example? Because you need to have some rules, and I just curious like where those rules come from.
Yeah. I know your question. Yeah. For this question, we just collect some for the position of two buttons, right? If their positions is on the left and on the right, let's say there's a button A and button B. If button A is on the left of button B on the phone, then we put button A on the left of button B on the watch. We just collect these constraints from the phone, and what the buttons looks like on the phone. It is not exactly, but similar similar positions on the watch.
I see. Thank you.
Okay.
Thanks. So another question on Jigsaw, right? I should mention that there are two Jigsaw papers in this session. We have the large language models meet program synthesis. We also have the
I think it's the large language models.
Yeah. So this one is about the large language model one. When feedback is given to Jigsaw, the learning effect is much enhanced, which is a positive development. How did you automate the integration of user feedback using Jigsaw in your research? Please unmute yourself, Naman.
Oh, thanks for the reminder. Yeah. So I'll quickly answer this one. When we were to evaluate the learning from user feedback component of a system, we organized a small hackathon at Microsoft Research India, where we conducted it over 2 sessions. So to evaluate the learning from feedback capability, we took the user feedback or the user fixes that people made in the first session, and we directly used them in and we did an offline learning phase, and we used the feedback in the next session. However, this process can be more frequent and probably online as well, where every time a user fixes some code, you can probably integrate the feedback to improve the learning from feedback capability. Does that make sense?
Hi, Jia. May I also have a question?
Yes, go ahead.
Yeah, thank you. If there's no question, I can take some time. I have a question for the paper analyzing the CMake build system, and I was wondering because you talk about a feature, the nested or expanding usage of variables, right? And I was wondering how is it different? Because to me, it's like a very common practice in many computer programs like Java programs or Python programs. So can you please explain? That why is this harder? Why is it a problem? That because it is not. There should be some solutions for other computer programs, right?
So if you want to have a comparison, it's not like Java or Python, but it's a macro in C. So when you analyze a C language, actually there's some pre-processing that is spanned on the macros. But when you do in CMake, for example, if you want to an analogy is you analyze the C program, but do not and execute like just take the program with macro and executing it, which is there are no existing work that's not what you do when you analyze C program. You make into a translation unit which span everything, include all the header files, and you have a translation unit. So it's everything already clear. And here in the CMake file, it's only clear at runtime when you know like what is this variable.
Can we split it like using some syntax knowledge to split them so that we can recover them back to a semantically equivalence?
For example, when you run the program with a variable x, and this x can take like either A or B, and this can only know at runtime when you really execute the CMake, and then later it can be expanded to, for example, AC or BC, depend on the value that you the flag that you pass at runtime.
Okay, thank you. I'll probably need to read your paper and to know more. Hi, as we have also questions from audience.
Yeah, I think probably I have also I have a question for Zhuangbin Chen. So I will first ask him the question, then we take the questions from the chat window. Yeah. So thanks for your talk. So you mentioned that your approach it's to facilitate the online anomaly detection, right? So when we're trying to detect the problems online, I think the efficiency is very important. And I see that in your evaluation, you mostly focus on effectiveness. So what about the efficiency? What is the cost of your approach? Thanks.
Yeah, thank you for your question. Well, I actually had a complexity analysis in my paper, and the most complex part of our algorithm is the offline chaining, which is O square, which is of quadratic complexity, but you have some like approximation ways to accelerate the process. However, for the online anomaly detection part, because I only use the parameters and data that I get from the offline stage, so the complexity for the online part is only O1, so it's quite efficient.
Thanks. That's a very good answer.
Thank you.
I think another question from the audience is already answered by Namajin in the chat window. So maybe I can.
Can I ask a question?
Yes.
Okay, thank you. I have a question for Naman. So I noticed that one of the input to your model is an I/O example. So if I want to use your model, do I need to an I/O example, to your model?
Yeah, so Jigsaw as a system does require additional specification in the form of input-output example. However, if you're just trying to use the language model like GPT-3 or Codex, or maybe the GitHub Copilot tool, for instance, these models do not require input-output example as a necessarily. However, it was so the case that we wanted some additional guarantees That is why we take this in product example.
Okay, sure.
Yeah, no problem.
So I have a question for Sanfeng. So it's interesting that you mentioned you haven't found any previous work that works on CMake. What do you think is the reason? If developers care about it very much, why no researchers are working on this? It's because I feel it's really strange. So what's your point of view on that?
I think that one reason is the problem really arise from industry, just like Facebook. So, for example, when you run static analysis, they mention that, okay, I run static analysis on this program, but they do not mention like what compilation flag because that the static analysis use, because eventually static analysis rely on some, for example, compilation database. It need to convert all the source code into abstract syntax tree so that it can do, for example, fixed point iteration or something like that, right? And the reason this problem arise because in industry we have something practice called shipleft. Like every time the engineer want to submit a code review, we want the static analysis tool to comment directly on the code review. So it only comment on the file changes. And when the static analysis expert, they can just choose some configuration to run to analyze. But many engineers they have different configuration. For example, I work on Android and the other might work on iOS. And the code, when it's cross-platform, it will select different files. So we cannot fix a configuration for static analysis. And the problem is we want to run static analysis as soon as possible to discover the issue as early as possible. So that's the practice called shipleft to the left of the software development. So I think because the problem arise from industry and is not much attention from academia.
Thanks. I hope your work will get more attention from the researchers so that.
Yeah. Thank you.
Yeah. Thank you very much for proposing that.
Yeah, I think there are quite a few research from academy on building system of other languages, but I'm also actually very surprised about this. Like, hardly see the studies on CMake.
Yeah. Is it because there are not many data sets, not any available data sets that researchers could work on because it's an industrial problem? So I wonder if, for example, big IT companies like Facebook, now called Meta, could publish some data sets. For example, the problem that you developers need when analyzing CMake, so that researchers could work on these problems using the data set.
CMake is not it's not like machine learning where you have data set. You can take any CMake program and analyze. The problem is the CMake language is very, very complicated. It has so many features and it had very quick iteration. Like they develop a new version every, I don't remember exactly, but every 2 weeks or every month they have a new version. And a CMake program is only use a sub feature of the CMake. So, for example, at the static analysis team at Facebook, at Meta, they support one CMake program, but then it cannot go to another system and just analyze. It needs to support the other feature. So the set of feature is very large.
And do you think the fragmentation is also, it's a follow-up question from Jia. I mean, do you think the fragmentation issue also will keep researchers from studying it? Because C++ has many different standards from C98 and C11, C++ 17 and 14. So many people, engineers couldn't figure out even one standard, and especially
Right.
for us, yeah.
Right. I'm aware that the problem for when analyzing C programs, but for CMake, I think that's so if you ask the questions is why they are not smart work from academia, I don't know. To be honest, I don't know. So the only work that I know is together with my co-author here. So they just give a proposal and we try to extend on that.
So I can you hear me?
Yes.
So I think CMake is just it's mainly used for C++, and it's just an ugly language, CMake, and there is no formal semantics for CMake. You could not find any formalism or anything on CMake, and the only way to understand how CMake works is look at the CMake compiler itself. And so it's just hard to understand it in the first place. In the paper, we outline several challenges on why it makes it so hard to formally analyze CMake, and it's confusing. And so because of that, I think that's the reason why not too many people attempt to formally analyze or even parse CMake files.
Thanks. I'm sorry,
But
I
that's
have
why we're
to.
here.
Sorry, I have to interrupt you. I need to leave to chair another session. So Jiawei, could you lead the discussion
Okay,
for the
sure.
remaining time?
I think
Yeah.
I think we have a question left. Yes.
So,
Is the
yeah.
is the integration of feedback manual work? And the question is from the question is from TimeView, right? So it's a manual integration of user feedback. I think the question is for Jigsaw, right? Language model.
Right. Yeah. So.
Yeah.
So I answered on the chat, but yeah, I'll just repeat here. So the user feedback integrations happens automatically after every few intervals. It was just the case that for our experiments and for our evaluation, we integrated the feedback like after the first hackathon session. In case of actual deployment, the integration should be more continuous so that we can reap the benefits of user corrections more quickly.
It's a question for myself, like because I read a paper in other field, like they use the feedback, they apply the reinforcement learning, but I haven't got the time to read your paper. But do you think that reinforcement learning is also a way of to implement the way?
Right, yeah, definitely. So you can definitely update the model, but in our work, what we wanted to do was, suppose you just have a black box API access to the model without access to parameters or access to fine tuning the model. In that scenario, how can we build a nice system which has nice performance? And therefore, we restricted ourselves to like learning program repair, like traditional template-based program repair strategies. So, which is why we used program synthesis-based user feedback learning.
Oh, okay. Thank you very much. And do we also have questions for other papers?
I have one more question.
Yeah, please.
For Chong. So I am wondering, how do you get the complete widget at the very first place? I mean, how do you extract the complete icon from the phone screen?
No, we just not extract the icon. We just dump the runtime pixel. Yeah, we have an instrumentation service in the app. We have to instrument the app, and our tool is just based on the open source app. So we instrument the app by adding our components, and these components at runtime just dumps the pixel, the runtime pixel of every icon, and then it transmits this icon data to the watch.
Okay,
and it can render on the watch.
Mm-hmm.
Thank you.
Thank you.
I know that there are some techniques about object detection or segmentation of images. Did you use that approach? Yeah. So segmentation of images. So you take the screenshots at input and output different icons, automatically extract data.
No, we just take the instead of segment, we don't use a full screenshot. We just take the screen. We just take a pixel of a specific icon. We do not use any image segmentation or
Oh,
image
okay.
detection.
Okay, thank you very much.
We have a segmentation, but not for image or not for object detection. Just our segmentation is just for the whole UI, to segment the whole UI into several